Welcome to the engineering class for November the 4th. I have looked over the homework that you guys submitted, and I saw that most of you did okay. The average score on the homework wasn't quite as high as it has been in the past, so I'm a little concerned about that. But there were still plenty of people that got it right, got them all right. Not very many of you attempted the extra credit problem. It wasn't that bad. Those of you that did attempt it, it sounded like you were just guessing, but your guesses were pretty good. So I gave you at least some of the extra credit, if not all in some cases. Let's just take a minute and go over the thing there. Give me a sec to get it ready here. Okay, so here I'll share my screen with you. Okay. All right, so if we go into the engineering class, all right, and modules. Okay, so don't forget about engineering day at the U, guys. That's a great thing. Even if you weren't getting extra credit for it, it's worth doing. They have some amazing labs up there, and the chance to connect with the professors is really a great experience. So even if you didn't get extra credit, you should do it. But you are getting extra credit, so you should definitely do it. All right, so okay, first couple questions. What is voltage? All right, well, there was more than one correct answer. Some of you picked one answer and then you stopped there. So it's not a measure of how much electrical charge a battery contains. I mean, you can have a big battery and you can have a small battery. They both have the same voltage, even though the big battery has much more charge in it. Voltage is a matter of the pressure. And so and the bottom answer is the one that most of you went with. But if you look at it, the second answer, it's also a measure of how strongly the battery pushes the electrons. So the more pressure a battery has, the more it's going to be pushing the electrons through there. So there were two answers for that one. You should have gotten both. Okay, so the current, all right, so a measure of how many coulombs pass each point in a given second. So we talked last time about what a coulomb is. You need to know. A coulomb of electrons is kind of like a gallon of water. You know, rather than counting the individual electrons, which would give you an unbelievably large number, we define this quantity and we just say, okay, it's a coulomb is that many of them. So yeah, so when we say that there's 3 amps flowing, what that means is there's 3 coulombs per second. So the first answer is definitely right here. It's definitely not how much it pushes back. That would be resistance. A measure of how much electricity is flowing through current. Yep, okay, it sounds like we got 2 answers. And you can see up here, I did tell you, I did warn you, there's more than one correct answer. And then how much electrical pressure? Well, that would be voltage, not current. So it's not that one. Okay, so then how about resistance? Okay, well, it's clearly not how much electricity is flowing. That would be current. Measure of how much it weighs? No, that's just silly. Measure of how hot it gets? No, that's not it. Although it is true that the more resistance an object has, the hotter it's going to get in many cases, but not all cases. So if you picked this one, I could understand why you might think that, but really it's just the last one. It's a measure of how much it pushes back. So number 3 was a potential confuser. So I figured since I gave you one answer that was obviously wrong, I have to give you at least one that might have been right. So in this case, although there could theoretically have been more than one answer, in this case, there was only one answer. Okay, so the electrical characteristics with the units. Well, voltage is easy. That's just volts. Anybody could have guessed that one. Current, okay, that one is going to be amps or some combination of them. We frequently use milliamps or microamps or something, but they're all just variations of amps. And then resistance, well, that one's going to be ohms. Okay. Okay, which one is false? An amp is the same as an ampere, and that sounds true to me. When a switch is open, it behaves like an open door and allows electricity to flow through it. Ah, that's the one that a lot of people get that one wrong. And understandably, I think when the electrical engineers set this all up, if I were them, I would have worded things a little differently because a lot of people think that's confused or get confused by that. So don't think of a switch as a door. When think of it as the circuit. If everything's connected, it can flow. And if the circuit is open, then the electricity can't flow. And so think of it that way. And then the rest of them are all true. Okay, so question number 6. We've got a whole bunch of batteries or a whole bunch of resistors, and they're connected in series. So hopefully you remember what we talked about last time is that means that they are all just connected in a line. So if you were to draw the schematic symbol for that, okay, so here's the battery, and I'm going to use this symbol for battery. That's what you're going to see on schematics. It's a shorthand way of saying battery. The long one is the plus side of the battery. The short one's the minus side of the battery. So if we connect up all these resistors in series, what it means is just one after the other after the other. Okay, and that one's really easy. All you have to do then is just add them up together. All right, so you got 5,000 plus 2,000. So the total is 7,000. And so then once you know that, then so now you can treat it like it's just one battery and one resistor. So the battery there is 9. The total resistance is 7,000. So when you work that out, okay, so you need to know Ohm's law, which hopefully you now know it. I mean, we talked about it. I gave you a reading assignment. So hopefully you know that the current is given by voltage divided by resistance. So if the voltage is 9 and the resistance is 7,000, so that gives so my calculator says 0.001287 and a bunch of more. Okay. Now we're only allowed 3 sig figs. So that means I have to cut it off right here. So am I going to round up or am I going to round down? Well, hopefully you see that this is closer to 129 than it is 128. So I'm going to round up. So 0.00129. Okay, but it says here it wants the answer in milliamps, not amps. So whenever you're using Ohm's law, the numbers that you put in and the numbers that come out have to be in standard units. They can't be milliamps or microvolts or kilo ohms. It has to be regular volts, regular ohms, regular amps. So this number is in amps. So if I want it in milliamps, that means I need to move the decimal over 3. So 1, 2, 3. So the answer works out to be 1.29. That's what I'm going to put in as my answer. And I was surprised at how many of you didn't get that one. A lot of you just left it blank. That was kind of a surprise. But this one's pretty straightforward. That's the answer. All right. Question number 7. So in this case, you were supposed to build the circuit in Tinkercad and measure the current. And in this case, when you did it, the current that you measured should have matched the prediction perfectly. So the answer for number 7 should have been the same as the answer for number 6. Okay. Now, question number 8. Okay. This time, it might look like it's the same question, but this time, instead of 5 kilo ohms, it's now 5 ohms. And instead of 2 kilo ohms, is now 2 ohms. Right? So the total resistance then is not 7,000 anymore, it's just 7. So then when we do Ohm's law, we get I equals V over R. So V is still 9. R this time is 7, not 7,000. And the answer works out. So on the calculator now it says 1.29. And that's amps. This time it's not milliamps this time, it's amps this time. And that's what I asked for the answer in. So the answer here, 1.29. So same number as before, except this time is not 1.29 milliamps. This time is 1.2 amps. All right. And again, although many, if not most of you got this right, the percentage of you guys who either got it wrong or just left it blank has me a little concerned. All right, and then question number 9, this was where you were supposed to take the Tinkercad circuit that you'd made previously and just, all you have to do is just change the resistor values. So just click on the resistor and change it from 5 kilo ohms to 5 ohms. And same thing on the 2 kilo ohm resistor. All right, now this time when you measured it on Tinkercad, you find out that the current that you get is not what you predicted. Okay, so the last question here is, why is it that you get less current than you predicted? And some of you made some pretty good guesses. In fact, I'm going to pick on one of you here. I hope you don't mind. Hey, Dan, I liked your guess. Would you mind unmuting yourself and telling us why do you think that the actual current was less than the predicted current? Earth calling Dan, come in, Dan.
Are you talking to me?
No, I'm talking to the other Dan. Let's see, Katoa, Cole Katoa. I thought you went by Dan. Am I wrong there?
I don't go by Dan.
Oh, I what do you go by?
Joe.
Joe. Oh, I'm sorry. For some reason, I got in my mind that you went by Dan. Okay, so I'm sorry. So Joe. Thank you, and I'll try not to make that mistake again. All right, so Joe, I liked your guess. What did you think was the reason?
So the what I put or like what I typed in the thing, I thought I'm not 100% sure, but I thought that the power supply might have overall had a stronger voltage due to the fact that you can change it like using the twisty thing. Sorry, I don't know what that is. And but on the 9 volt battery, it's only a 9 volt. You can't really change it, and that's why I thought that having the power supply might be a stronger voltage.
Okay, I like your thinking there. I would change the wording ever so slightly, but the overall thinking I would agree with. It's not, if you've got a 9 volt battery, if you got a power supply set for 9 volts, it is putting out 9 volts of pressure. So the pressure of the 9 volt power supply will be the exact same as the pressure of a 9 volt battery. Now, the thing is that the power supply is capable of putting out more. If you were to crank that knob up, you could go to 10 or 11 or 12 or whatnot. The power supply is capable of providing more. But if you set it for 9, then the voltage that you get is not stronger than the voltage that you get out of a 9 volt battery. But the thing is that the power supply has the capability to push more current out. I mean, think of it. Well, let's see where. Okay, so here's a AAA battery. All right, so it's got electricity stored in it, and if we connect it up to a light bulb or something else, electricity could flow. But the electricity inside this battery, it's not just free electrons just sitting there waiting to go. It's chemicals inside. And these chemicals undergo a reaction that gives off electrons. And it's only going to give off electrons until it builds up a pressure of 1.5 volts. Once it reaches that pressure, the chemical reaction inside here stops because the pressure of having all the free electrons, it pushes back. So you got a chemical reaction trying to free up electrons, but then you have a bunch of free electrons opposing that. So you've got inside the battery, you got kind of a little war going on here. The chemical reaction is trying to produce electrons, and it can up until you get to a point where you get a certain number of electrons, and then they push back. So then the chemical reaction stops. All right, so if you hook this up to a light bulb or whatever, and so the electricity starts flowing, that kind of relieves the pressure a little bit, and that allows the chemical reaction to take place to create some new electrons. But chemical reactions take time. And so if you pull electricity out of this battery too fast, the chemical reaction can't keep up with that. And so the voltage is going to drop. And a power supply works differently. It doesn't work off of chemical reactions. It works off of taking electricity out of the wall and converting it into a different type, a lower voltage electricity. So the power supply doesn't depend on chemical reactions taking place. So if you pull current out of there really fast, it can replenish the supply really easily. And so that's the way that I prefer to word it. But Joe, I liked your thinking there. I thought it was a darn good guess. And the way you worded it, I liked 99% of the way you worded it. There's just one little tiny thing that I would have worded differently. But okay, so there's last night's homework. Those of you that didn't get a 10, hopefully now you know why, and hopefully now you understand what the right answer is. Okay, so today we're going to go into this a little bit further. We have already talked about how to connect up resistors in a way that we call hooking them up in series. And that one's really straightforward. I mean, so if I've got a battery over here, let me switch to a little bit thicker pen, a little easier to see. So here's my battery, and I've got two resistors. So there's the first one, there's the second one. Okay, so if I hook this up like this, it's called series. And series is really, really easy to deal with. The total resistance is just whatever the two are added together. So if we call this guy R1, call this guy R2, so then R total is equal to R1 plus R2. And if we had an R3, then let's say plus R3, and then plus dot, 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 dot. As long as they're hooked up in series, you just keep adding them. And that tells you what the total resistance is. And so then if you wanted to, you could take this circuit that has multiple resistors, and you could replace it, at least in theory, with one resistor, where the value of this one resistor, we call it R total, and is just the sum of all these. So even though the one on the left here, this might be the real circuit, this one on the right here is what we call the equivalent circuit. Okay. And the thing is that the battery over here and the battery over there, they can't tell the difference because batteries don't have eyes. They can't look over there and see how many resistors are there. Batteries can only feel how much resistance. So you got a battery trying to push electricity through there, and there's something there pushing back, so the battery can feel the resistance. So the battery on the left is going to feel the exact same resistance that the battery on the right is. Okay, so we call these equivalent circuits. And if you're dealing with resistors hooked up in series, it's really, really easy. But there is another way to hook up resistors. And so that's what we're going to talk about today. Let's say that I have my battery right here, and I've got my resistor right here. And I want to add in a second resistor. But instead of putting that second resistor in the same path where the first resistor was, I'm going to add a new path. So in addition to adding the resistor, I'm adding in some wires that weren't there before. Okay, so let's call this guy R1, let's call this guy R2. So I have added in a new resistor. Now, a lot of people think, well, okay, it's just going to behave like before. So they're going to think R total is just going to be R1 plus R2, but no, that's not the way it's going to be. Because in addition to adding in this new resistor, I also added in a new path that wasn't there before. And so if you look at the electricity flowing through here, okay, so let's say that we have not yet added in the new resistor. All right, so here is our battery, and it's trying to push electricity through here, and it comes to a resistor, so the resistor pushes back, and the battery, you know, the battery is able to get the electricity to flow, but it has to fight against that resistance. So you don't get as much current flowing as you would if that resistor wasn't there, okay? So if I now add on a new circuit or a new branch to my circuit that wasn't there before, okay, what you'll see is that the same current that was flowing through here before I added that new circuit, before I added the new resistor, that same electricity is still going to flow through there. But in addition, we also get some new electricity flowing through here. Okay, so even if this resistor is a really massive resistor, even if this is like a 1 million ohm resistor, okay, so it got a tremendous amount of resistance. Still, there is going to be some current flowing through here that wasn't flowing through before, and that's on top of the current that's still going to be flowing through this guy. And so what the battery is going to feel is the battery is going to feel less resistance. Even though you added on a resistor, the battery is going to feel less resistance, which you got to think about for a little while before it makes sense. How is it possible that adding a resistor can reduce the resistance? Well, the answer is because you're not only adding on a resistor, but you're also adding on a new path that wasn't there before. Okay, so it actually is true that the resistance goes down when you add a new resistor if you connect it in parallel. Okay, so if we can't use this equation up here to figure out what's going on, well, what equation could we use? In fact, tell you what, let's just clear everything out here. Okay. So here's your battery. Here's your one resistor. Let's call this R1. Here's your other resistor. Let's call this R2. Okay, so I know that some of you know the answer here. Anybody, how about Marshall? Would you be willing to tell us how do we calculate the total resistance when they're hooked up in parallel?
Isn't it like all of the resistors added up over 1,000? I can't remember.
Close. How about Don's? What do you think?
I have no clue.
Okay, Luke, calling on you. And you better know the answer because you're in my electronics class.
How to solve this? It's
how do you calculate the resistance?
how to calculate the resistance. So
Go.
you're gonna have to go 1 over the resistance plus 1 over the resistance. So
Okay.
Or you can do 1 over the resistance plus 1 over the resistance to the negative first power.
Okay. All right. So what he's saying here is that instead of using the formula that we had before, so R total equals R1 plus R2. Okay, we can't use that. We can't use that one. Okay. So what we're going to do instead, hang on just a second. I just did something really funny to my screen and I'm not quite sure how I did it. Okay, there we go. All right, sorry. I've got a bunch of windows on my screen that you guys don't have on yours, and I accidentally touched one of the windows and it got really weird. Okay, so let's go back to where we were. So we can't use this equation that we used before because that only applies in series. But if we just put 1 over everything, so instead of saying R total, we say 1 over R total. And instead of saying R1, we say 1 over R1. And instead of saying R2, we say 1 over R2. Okay, so if we do this, then it works out. All right, so let's try an example here. Let's suppose this is a 12-volt battery, and let's suppose that this resistor here is 150 ohms. This resistor here is 225 ohms. Okay, so first off, if all we care about is the total resistance, we don't care what the battery is. Doesn't matter if it's a 12-volt battery, a 9-volt battery, or whatever. If all we care about is the total resistance, we can ignore the battery and just look only at the resistors. And so what we're going to get then is 1 over R total is equal to 1 over 150 plus 1 over 225. Okay, so when I put that in my calculator, so I get 1 divided by 150 plus 1 divided by 225. Okay, so I get 0.01111. Okay, so now I ask, is that our total? To which you reply, no, that's not our total. This is 1 over our total. So how do I get 1 over our total? Well, if I just flip it, okay? So if I flip this side, okay, so that I want to get R total over 1, which is just same thing as R total, okay? If I flip this side, well, I can flip the other side. Now you say, well, how can I flip it? I don't have a fraction to flip. Well, hopefully you guys realize that any number is the same thing as that number over 1. So this number that we have here is really the same thing as that over 1. So I can, in fact, flip it. Okay. So our total then is going to equal 1 divided by that number. Okay. So if I ask in my calculator, okay, what is 1 divided by that number that I just got through calculating? You'll find out that the answer works out to be 90. Okay. So the total resistance now is 90. And notice that that total resistance is less than any of the resistors. I mean, this guy here was 150. This guy's here is 225. So when I added on that resistor, my total resistance is less than any of the resistors, and that will always, always, always be the case. Okay. If you have a bunch of resistors hooked up in parallel, whichever resistor has the least resistance, the total resistance is going to be even less than that. Okay, so this is the formula that you want to use. Write that down, put it in your notes, memorize it, tattoo it on your arm, whatever it takes to learn that. Okay, now I don't think I'm going to take the time to derive that. In my physics class, I think deriving important equations is really important. I think it's important to know where they come from. But this isn't my physics class, this is my engineering class. So I think I'm going to just let you just play with the experience with it and see if it gives you the right answer. You know, maybe build some circuits in Tinkercad and then predict what you think the current should be. And then when you build it in Tinkercad, then measure the current and see what it actually works out to be. And now I just talked about measuring the current, which we haven't done yet. So we need to take the one more step here. So let me go over to here. Okay, so let's redraw our circuit here because it was getting pretty messy before. Okay, so we've got a resistor, we got a circuit now that actually has 2 resistors on it, but as far as the battery concerned, it might as well just be 1. Okay, because the battery is going to feel the same resistance as if we replaced all of those other resistors with one 90 ohm resistor. And so if it's a 12-volt battery and we want to know how much current is going to flow, well, we use Ohm's law. I equals V over R, which is the other thing that you should have memorized by now. Okay, so if V is 12 and R is 90, then I get, my calculator, I get 0.1333 repeating, okay? And so I could just say that that's my answer. I could just say that's how much current is going to flow. Now, most of the time, electrical engineers, they don't, for whatever reason, they don't like numbers that are less than 1 or greater than 1,000. And so what they do is they use the milli or micro or kilo prefixes in order to adjust it so that the number that they type into the answer box is usually always a number between 1 and 1,000. So this number here is less than 1. So how could we, what units would we use in order to make it so that the number we type into the answer box is a number that's between 1 and 1,000? Well, if we just take this, the decimal, and we move it over 1, 2, 3, so there it is, then that will tell us how many milliamps we have. So 133.3 milliamps is equal to this number of amps. So electrical engineers get a lot of practice at converting between milli and kilo and micro and giga and all that stuff. They do it a lot. So you guys need to be really good at it too. So if I were to give you a test where I would say, how many volts is 13.9 kilovolts, okay, you should know Well, do you move the decimal to the left 3 times, or do you move the decimal to the right 3 times? You guys should be really good at that. And I realize that you might not be. So let's do a little bit of unit conversion problems. Let's take that one that we just did. So let's say we've got 13.3 kilovolts, and I want to know how many volts that is. So let's use the Ames method for unit conversion. And so your science teacher should have already talked to you about what's called the Ames method. And the way it works is that we take the number we've been given, and then somewhere else on the sheet, we write how many volts equals how many kilovolts. And so hopefully you know that 1,000 volts equals 1 kilovolt. Okay, so then over here, we put our parentheses in a horizontal line. And one of these guys goes on top and the other one goes on bottom, but how do you know which one goes where? Well, if we've got 13.3 kilovolts, that's the same as 13.3 over 1. So the kilovolt is on top. So when we convert it, we want it so that the kilovolts are going to be on the bottom so they cancel out. So it means this guy needs to go on the bottom. So 1 kilovolt. So that way kilovolts cancels kilovolts, good. But we have to take whatever it's equal to and put it up on top. So 1,000, it goes on top, and that's volts, and don't forget the units. Okay, so then we know that the answer is 13.3 times 1,000. And so now we know that what we do is we take the 13.3 and we move the decimal over 1, 2, 3, there it is. So we have to add 2 zeros, so there. Okay, so you get really good at converting units. We're gonna be doing that a lot. That's something the electrical engineers have to, it just has to be second nature to you. You have to have done so many of them that you can just do it without thinking. All right, so let's do a little quiz here. What I'm gonna do is I'm gonna give you guys a problem, and I want you to type the answer into the chat box, but I want you to type it in using a private message, not a public message. I don't want the other people to see what your answer is. Okay, so we're going to take a circuit that looks like this. It's got 3 resistors in it. All right, and so this resistor here is 210 ohms. This resistor here is 175 ohms. This resistor here is 350 ohms. This battery is 9.0 volts. So there's 2 questions that I want you to answer. First, I want you to tell me what is our total. So what I mean by that is, if we were to take the real circuit and we were to replace it with an equivalent circuit that only had 1 resistor in it, what would the value of that resistor have to be so that this battery and this battery feel the same resistance? So question number 1, what is our total? Question number 2, I want you to tell me how much current will the battery put out in this case. Don't worry about the current that's flowing through here or here or here. Don't worry about that. I just want to know how much current is the battery putting out in this case. All right, so I'll give you a minute to think about that. And when you get the answer, type it into the chat box, but use a private message, not a public message. Okay, Luke, I need to know the current too, please. So far, I'm only seeing 2 answers. Still only seeing 2 answers, guys. Now, the two answers that I'm seeing are the same answers, so that's encouraging. That doesn't guarantee that they're right, but it is certainly increases the odds. Okay, I just saw another answer, and that one is different from the first two. Now, it could be that you're right and they're wrong. That has happened before. Okay, I just saw another one that's different still. Oh my goodness. Now I'm starting to see answers that are all over the board here. Okay. Okay, good. There's another answer that matches the first two. That makes me feel a little better. Okay. All right. So tell you what, let's see, who are the first two people to give me an answer here? So Long Walk Presley. Love that name. Okay, so Long Walk Presley, can you walk us through how did you do this?
How did I know you would pick me?
Well, because you were the first one to put an answer in. That's
Yeah,
why.
I know.
So maybe that's a punishment, isn't it? I should be careful. I don't want to punish people for being first. Okay, so tell us, how did you get it?
Okay, so whenever I'm doing this, especially with parallel circuits, I always make sure to, in my calculator, I make it a few equations, but you could technically do it with one, though I wouldn't recommend it. So what I do is first parenthesis 1 divided by 210.
Okay, hold on a second here. Let me write this down. So parenthesis 1 divided by 210. Okay, got it?
Okay, end parenthesis,
Oh, in
plus
parenthesis?
end parenthesis,
Oh, okay,
plus
wow.
parenthesis. Well, I just do that as just to make sure. You don't
Okay.
really need the
Yeah,
parentheses.
yeah, it turns out in this case, you don't really need the parentheses. But the thing about parentheses are if you put them in, even though you didn't need them, it doesn't hurt. Whereas if you leave them out in cases where you do need them, it does hurt big time. So I agree with you, Presley. When in doubt, put them in. Hey, fine.
So the next part is 1 divided by 175, end parenthesis, plus begin parenthesis, 1 divided by 350, end parenthesis.
Okay.
Then you calculate that.
All right. And so when you do, you will get, let's see, 0.01333 repeating.
Yeah.
Right. Okay.
Then I take the answer from that, and it's called invert. I think we covered that. Not 100% sure. But it's basically just to put it up to the power of -1.
Okay, so there's a key on your calculator. If you have a TI-83 or 84, it's on the first row. It's the fourth one down. It says X -1. So that's the same thing as saying 1 over X, which is what we want. Well, we want to take this number and we want to do 1 over that number. Okay, so if you just push this key right here, it'll do it for you. Or if you want, you can just go ahead and type 1 divided by and then put in that number. Very good. And then what did you get when you did that?
So after you do that, you get 75.
Okay, so that means that our total is 75. Okay, so if we were to take all three of these resistors and replace them with just one, as long as that resistor is 75 ohms, this battery here and the battery up here would not be able to tell the difference. Make sense? Okay, so once we know that, then we can use this circuit here to calculate how much battery or how much current the battery puts out. And we just use Ohm's law for that. So I equals V over R. V is 9, R is 75, and our answer works out to be I equals 0.120. Okay, and the numbers that come out of Ohm's law are always going to be for current anyway. They're always going to be amps, not milliamps or kiloamps or microamps or anything. They're always amps. So you could say, well, here's the answer. We're done. We can stop right here. And I couldn't mark you wrong if you did that. Okay. But electrical engineers generally, you know, like I said, they like their numbers between 1 and 1,000. And this is not a number between 1 and 1,000. Okay. So Luke, how do I take this number here and turn it into something that's between 1 and 1,000?
So since it's already in amps, or if you want to turn it to milliamps, you just times it by 1,000 because 1,000 milliamps equals 1 amp. So
Okay.
therefore, dividing it by 1,000 will turn it into milliamps.
Okay, so he's claiming the 1000 milliamps is equal to 1 amp, which I agree with. And so then we can look at this, we can say, all right, so that cancels that. So we know that we want to multiply by 1,000, not divide. I mean, I see this all the time. People, when they should multiply by 1,000, what they do is they divide by 1,000. So if you write it out like this, then you'll never go wrong. So we know that we want to multiply by 1,000. So that means we want to move this over to the right. 1, 2, 3. Okay, so the answer then is going to be 120 milliamps. Bingo, we're done. All right. So some of you, you've done stuff like this before. You know, you've either taken physics or electronics or some other class, so that you're really comfortable with converting units here. I realize that others of you may not be quite so comfortable, but hopefully when you do the assignment tonight, that'll help you be more comfortable. Okay, one more little twist that we want to put on here is that it's possible to hook up resistors that are in a combination of series and parallel at the same time. So let's see how we could do that. Okay, so let's suppose that I have a resistor network that looks like this. So here's my battery. And so here's one resistor. And then here at this point, it splits like this. Okay, so this might look really weird, but it's actually not that bad. Okay, so let's suppose this guy, so let's call him R1, and let's say that he is 175 ohms. This guy over here, R2, let's say that he's 350 ohms. And this guy here, let's call him R3, and let's say that he's 310 ohms. And so I want to replace these guys with an imaginary equivalent circuit that only has one resistor in it. And I want to do things so that this battery here and this battery here, they both feel the exact same resistance. Okay, so I want to know what is our total, but it's not purely series or purely parallel. It's a mixture of the two. All right, so here's how you approach it. What you're going to do is you're going to get an intermediate circuit. So combine these two guys together because these guys are connected up in parallel. So we're going to combine them together to make an intermediate circuit that looks like this, where this resistor is the equivalent of these two guys put together, and then this resistor is just that guy straight without any changes whatsoever. Okay, so what we recognize is that these two, whoops, I hate it when I do that. I forget that I'm still in erase mode, not in draw mode. Okay, oops, try that again. Okay, all right. So these two guys are hooked up in parallel. So if we want to know what this guy is, we can use the parallel thing. We can say 1 over R1 plus 1 over R2 equals 1 over R total. And now this is not the final total. This is just the subtotal. All right. So 1 over 350 plus 1 over 310. All right. So that is equal to 1 over R total. So let me see. So 1 divided by 350 plus 1 divided by 310. So this number works out to be looks like 9.216 times 10 to the negative 6. Okay, so it's in scientific notation, but that's okay. I can deal with that. So then just hit, so this is 1 over our total. That's not our total. So if I just hit the X inverse key on my calculator, it'll take whatever was my last answer and it'll raise it to -1. So, whoops, I did something seriously wrong somewhere. Oh, I know where I went wrong. Sorry. I hit the wrong key on my calculator. Let's try that again. Okay, so 1 divided by 350 plus 1 divided by 310. Okay, so yeah, I'm getting a very different number this time. It helps if you hit the right key on your calculator. Okay, so I get 0.00608 and change. Okay, but this is 1 over our total. So if I just hit the X inverse key, or I could do 1 divided by that. So I just hit X inverse. Okay, so it tells me 164. Okay, so if I take these 2 resistors and replace them with 1 resistor over here, where this guy is 164 ohms, and this guy is the same as that without any changes at all. So he's 175 ohms. So now I have 2 resistors that are hooked up in series, and series is really easy because with series, all you have to do is just add them. So R1 plus R2 equals R total. So I take my last answer, add 175, and so I get 339. Okay. So if I were to replace the real circuit over here, which is kind of complicated, with a circuit that only had 1 resistor in it, as long as the value of that resistor is 335, the battery on the right and the battery on the left would not be able to tell the difference. And so then if I want to know what the current is, then I just do I equals V over R, and that'll tell me what the current is. So I'm not going to bother taking the time to do that. Okay. So does this make sense? If I were to turn you loose and let you work on the assignment tonight, you have confidence that you'd be able to do it? Okay. So here is the assignment for tonight. It's in Canvas. Let's go to here. So click on modules. I guess I said here is a little prematurely here. All right, so let's go down here. So resistors connected in series and parallel. That's your assignment for tonight. I do have a couple web pages that I highly encourage you to read. I'm not going to require it because I don't think it's so complicated that it needs a written explanation. But if you didn't fully understand what I just said, and you say, well, I wish there was somewhere I could go that I could read that would tell me about it. Well, there is. Okay, so go to this link right here to learn about connecting series resistors in series. Go to this link right here to learn about how to connect resistors in parallel. Then once you've read that, then here's a bunch of questions for you. Here's a circuit that looks awful familiar. Where have we seen that before? Okay, answer these questions and I think you'll be in good shape. So if you don't have any questions, I'll let you go ahead and get started on it. Remember, the period is not over. We still have 30 minutes left before the class period is over. So hopefully, if you get to work on it, you can finish this assignment before the bell rings, and then you won't have any homework. So if you're good, you can just go ahead and type bye into the chat box. If you want to ask a question, here, I'll turn off the recording so that you can ask it without being embarrassed.